Perceptively, Maxwell added that Faraday sought the seat of the phenomena in real actions going on in the medium. Of course, as it would later be seen, the medium is the electromagnetic field, and that's where the action really is. But before Maxwell could get the message from the medium, he had to determine whether waves could travel through the electric and magnetic fields at the speed of light. If so, they would have to obey the 4 laws of electricity and magnetism.
The electric flux through any closed surface is equal to 4 pi k sub e times q, or q over epsilon naught, where q is the total charge enclosed by the surface. And the magnetic flux through any closed surface is always equal to 0. These are Gauss's laws for electricity and magnetism. The circulation of magnetic field around any closed path is equal to mu naught times the electric current passing through that path. This is Ampere's law. The circulation of electric field around any closed path is equal to minus the rate of change of magnetic flux through that path. This is Faraday's law of electromagnetic induction.
So suppose that there can be a wave in the intensity of the electric field. This one's a transverse plane wave, and it travels, of course, at the speed of light. But consider the field at any one instant. Since it's up in one region and down in the next, it has a circulation about this path. According to Faraday's law, that means that there must be magnetic flux through that same path, and furthermore, that it must be changing in time. And that can only mean one thing. A magnetic wave must tag along with the electric wave everywhere it goes. But, and here's the crux of the problem, that in turn means at any instant there's a circulation of the magnetic field about this path. And according to Ampere's law, that can only be true if there's current flowing through it. But in empty space, there's no matter and no electric currents. So there's no way around the fact that according to the laws of electricity and magnetism in Maxwell's time, there could be absolutely no electromagnetic waves in space. The point was this: if the laws of physics stated that waves couldn't exist in empty space, could it have been that, as fundamental as they were, those laws were somehow incomplete? Maxwell's task was to examine the fundamental laws of his era, and his triumph was to find the missing piece. And he did so, by looking into a simple and altogether conventional apparatus, the capacitor. The magnetic circulation around any path depends on the electric current linked through the path. The only way to be sure that the current goes through the path is to imagine a membrane bounded by the path. Then the same current must pass through the membrane, no matter what shape the membrane takes. But that's no longer true if the current flows into a capacitor. Then, even though current is flowing, there may be none through the membrane. If so, what is the magnetic circulation equal to? Seeking an answer to that question, Maxwell took a page from Faraday's book. Changing magnetic flux creates electric circulation. And then, as usual, he looked at things the other way around. Could changing electric flux, he wondered, create magnetic circulation? The answer promised to solve the capacitor problem.
As current flows into the capacitor, charge builds up, which creates an increasing electric field between the plates. The electric flux through the membrane can be deduced from Gauss's law by imagining a closed surface. All the flux goes through the dome-shaped membrane, and it's equal to the charge on the capacitor plate over epsilon naught. The rate of change of electric flux can be found by differentiating both sides of the equation. It's given simply by the current flowing in the wire. In other words, epsilon naught times the rate of change of electric flux through the dome-shaped membrane is the same as the electric current through the flat membrane.
This was Maxwell's crucial discovery, the precise manner in which changing electric flux can generate a magnetic field as if it were a kind of electric current. In fact, Maxwell himself called this mathematical term the displacement current. In other words, the magnetic circulation around a closed path is given not only by the electric current through it, but also by the rate of change of electric flux through it. This was how James Clerk Maxwell completed the laws of electricity and magnetism. And with these laws, Maxwell could show that electromagnetic waves of every frequency and wavelength would propagate through empty space at the speed of light. Maxwell's discovery, which seemed purely theoretical at the time, would lead to the sights and sounds of the 20th century, radiating through space not only as visible light, but also as radio waves, microwaves, and the entire electromagnetic spectrum. It was a discovery that would lead far beyond the Earth into the deepest reaches of space, where a wave in the intensity of the electric field implies the existence of a changing magnetic flux. That means a wave in the magnetic field. And that's made possible by changing electric flux. And it's made clear only because Maxwell understood that electric and magnetic fields create each other if they move in a wave together at the speed of light. And so it goes, in lockstep through eternity, both fields propagating throughout the universe. And in that light, always at the speed of light, one can finally see the power and the glory of Maxwell's equations.